Hello, my name is Tony Ichite, and this is my presentation on computer vision for dating historical objects and photographs. Essentially, through this presentation, I'll be demonstrating ways that computer vision can help historians, archivists, archaeologists, museum workers, and forensic specialists, and things of that type to date historical photographs and objects just through the use of computer vision. This work seeks not to replace the worker, but to help them out in their everyday tasks. So our problem statement lies in how expert dependent um, uh, traditional dating methods are, as well as the fact that a lot of things are moving to digital formats. Um, and what we seek to do is train convolutional neural network models on historically dated image data sets. And our hopeful finding is that deep learning is a strong way of figuring out how to historically date pictures, as well as um, machine learning. The subject that I'm researching with my topic matters because historical dating is a very important um, tool in the field of history and other arts fields. Um, Historians can catalog and apply context and link evidence based off of when and where the data was formulated, or specifically here, how the picture was taken or when the picture was taken. It can apply for historian, archivist, or archivist, museums, and forensic teams. Historical data is a very powerful and interpretive method of, or historical dating, traditional historical dating is a very powerful and interpretive method of getting information on objects and materials these days. But the limitation is scalability. It is slow, dependent on individual expertise, and difficult to apply consistently across thousands or millions of images. A research problem that you run into um, working on this issue is that the data sets of historical data is fundamentally different than the ImageNet style data sets, meaning that a lot of the training images are from more modern times and more trained and tailored towards modern images. Our hypothesis is deliberately two-sided. It expects that convolutional neural networks can detect error-related visual patterns such as image structure, color, shape, texture, clothing, architecture, and materials. But it also expects that dating many objects requires cultural context that computer vision alone cannot provide. As the different types of convolutional neural networks are formed during the years through invention and innovation, um, you eventually arrive at AI for heritage, cultural heritage specifically, which is AI that can provide cultural context to your model. My theoretical framework is based off of digital humanities, and it basically asks the question if the model can say that certain visual features are statistically associated with a period, the historian must explain whether that association makes historical sense, checks supporting documents, and assesses cultural context. All of this is to say that the research gap is that not whether or not the convolutional neural networks work, but if they work for historical dating. My resulting data set uh, from setting up the model for the experiment is 10,000 images across 4 balanced time blocks, and a separate test set of 1,500 images. Of course, there's some data preparation that goes along with image preprocessing. Historical images are inconsistent in size, quality, brightness, damage, and format. Preprocessing reduces irrelevant technical variability. So our convolutional neural network model is a high-level architecture. Convolutional layers detect visual features, pooling layers reduce dimensionality, fully connected layers combine extracted information, and the output layers produce a probability distribution across historical time periods. This slide shows its importance in the way of demonstrating that not only do convolutional neural networks perform in isolation, they also perform against traditional learning models. These are our evaluation metrics. Accuracy is the shape of correction prediction. Precision tells us the reliability of a particular period prediction. Recall tells us whether the model can find all items from a period. F1 score balances precision and recall. This slide summarizes the experimental sequence. The pipeline begins with publicly available images, applies preprocessing, trains the models, tests on held out data, and then compares performance across convolutional neural networks, ResNet transfer learning, SVM, and random forest. As far as the model's performance, the ResNet transfer model reached 86.7% accuracy, the custom convolutional neural network reached 82.4% accuracy, random forest reached 71.3%, and SVM reached 68.5%. This slide just shows a more detailed review of those same metrics. This is a metric that shows which images were easiest to date. Historical portraits reached 88.2% category accuracy. Architecture and streetscapes reached 85.6%. Clothing and fashion 84.7%. Manufactured objects 80.1%. And document/manuscripts 76.9%. This slide shows the convolutional neural network's training dynamics across 50 epochs. The significance of adjacent period errors is if the model confuses late 19th century images with early 20th century images, this may reflect real continuity in fashion, architecture, and photographic style. This slide shows our key findings, but summed up, it shows that the most important idea is not that AI can solve historical dating perfectly, it is that AI can create a useful first pass, identify likely periods, flag uncertain cases, and help experts prioritize where to focus. In a practical sense, AI can automatically group materials, identify likely dates, recommend metadata, catch inconsistency, flag difficult cases, and this lets the curators and archivists focus on higher order interpretation and verification. As far as responsible use goes, it's good to note that even when images are publicly available, historical materials may include people, culturally significant events, or sensitive records. In a future agenda, future work should focus on larger and more diverse data sets, multimodal modeling, explainable AI, finer-grained data, and practical workflow studies. In conclusion, computer vision can support historical dating by making archive and analysis faster, more consistent, and more scalable.